So this is very much like what we've seen before. Now, consider this case here, where you have two measurements in a three-dimensional Hilbert space. And again, for simplicity, I'm just going to draw real amplitude states. And there are two different bases. So you'll notice that this guy's rotated relative to that guy. So I've called these psi2 prime and psi3 prime. But psi1 is common to both bases. OK. Well, what you might hope to do in that case is represent each of these by a set of indicator functions. But the indicator function associated with psi1 in this case should be exactly the same as the indicator associated with psi1 in the second case. What you notice is that the probability of getting the first outcome in this measurement is exactly the same as the probability of getting the first outcome in that measurement, no matter what preparation you do. So take any preparation you like, calculate the statistics, and find the probability of the first outcome here. It's always going to be exactly the same as the probability of the first outcome in the top case. And so that might lead you to think, right, so those first outcomes are measuring exactly the same properties of the system, so it makes sense to model it by exactly the same indicator function. So that is the traditional notion of non-contextuality, that every vector considered as a measurement outcome should be associated with the same indicator function, regardless of how it's measured, meaning regardless of which basis it's a part of. And you can think of the basis that a given vector is a part of as part of the context in which that vector appears. So this would be saying that the way you ought to represent a vector in the hidden variable formalism should not depend on that context. Here's a slightly different way of describing it, which is, again, a bit more standard for the older literature. For every ontic state and every basis of vectors, for every ontic state, every basis of vectors, so every measurement in quantum theory, should receive a 0-1 valuation. So that just means an assignment of zeros and ones to every vector, wherein exactly one element is assigned the value 1, and that element corresponds to the outcome that would occur if you did that measurement and the ontic state was lambda. Every vector is assigned the same value regardless of the basis it's considered a part of. So here's an example. Here's a 0-1 valuation for this basis. So it can only have a single 1. And what this means is that if you prepared the ontic state lambda and did this measurement, then lambda specifies that you would definitely get outcome 1, and you wouldn't get these two outcomes here. And so if I look at the previous slide, I mean, that's consistent with this. If I look at any lambda and I just sort of look at that point, then two of the outcomes are assigned 0, one of the outcomes is assigned 1. So instead of representing what the outcomes will be for all lambda, this sort of picture just says for a particular lambda, this is what it looks like. And then the assumption of non-contextuality says that if I consider another basis, which has some element in common, then whatever value I assigned in this basis, I have to assign the same value in this basis. Okay, so if it's 1 here, it's 1 there. And if it's 0 here, it has to be 0 there. Of course, where the 1 is assigned among the three elements could be different as long as these two agree. So it could be that this vector is assigned value 1 by lambda, and that same lambda assigns 1 to this vector rather than this one. But they have to agree on the places where they overlap. So that's just a completely equivalent way of expressing that traditional notion of non-contextuality. OK, so what's called the Bell-Cauchy-Specker theorem is the result that a non-contextual hidden variable model of the type I just described is impossible for Hilbert spaces of dimension 3 or greater. So you can't find models of the type that I just described. And so this was basically discovered independently by Bell and by Cauchy and Specker. Their paper on this was 1967. Bell's paper was published in 66, but was submitted in 64. So let me give you an example of a proof of the impossibility of non-contextual hidden variable models for projective measurements. So this is a proof due to Cabello and co-workers. It works in a 4-dimensional Hilbert space. and it uses 18 rays in that four-dimensional Hilbert space. And the idea is, so this diagram represents a whole bunch of different bases in that four-dimensional Hilbert space. So every color here is a basis. So if you look at these four vectors, for example, and you were to look at the overlaps of any pair of them, you would find that they're orthogonal. So these four guys are a basis. And similarly with every other four that are a given color. And some vectors appear in more than one basis. Well, actually, all vectors appear in exactly two bases. So every node here, which corresponds to a vector, has two colors associated with it. And this diagram is just a way of representing the orthogonality relations between these guys. So all the lines among nodes correspond to the fact that those nodes form an orthogonal set. And all the squares also tell you that those nodes form an orthogonal set. OK, so how does the proof work? Here I've just rewritten all of those vectors twice over. So I've listed all 9 of the orthogonal quadruples of vectors that we saw. If you counted out the number of colors, there were 9 of them. And so that means that every ray is appearing twice in this list because it appeared in, every one of them appeared in 2 of those bases. OK, so the assumption of a non-contextual hidden variable model says that every basis, I should assign zeros and ones to it such that there's a single element that's assigned 1 and the others are assigned 0. That would tell me which outcome I would get if I were to do that measurement with the hidden variables prepared in state lambda. And furthermore, if I assign a 1 or a 0 to a given vector in one basis, like say here, I assign a 0, 1 to this vector, then I have to assign the same value where it appears in every other basis. That's the assumption of non-contextuality, that the value you assign to it doesn't depend on which basis it's considered a part of. So now you can see that there's a problem, because if I have to assign a single 1 to every one of these columns, then in total I'll be assigning 9 1s. And yet every ray appears twice in this list. So if I want the same value assigned regardless of context, then if I'm assigning 1 to a bunch of rays, then every 1 I assign will appear twice in the total list, because that ray is going to appear twice. So that says that there should be an even number of 1s, not an odd number. So you have a contradiction. So you cannot assign zeros and ones such that the value you assign is independent of which list it appears as part of. Questions? So I don't expect you to have gone through your head and verified the orthogonality relations and so on. But so I'm asking you to trust me that the orthogonality relations are as I say. But it's certainly plausible that quantum theory could admit of such a set. And so Cauchy-Specker constructions are about finding these sets. And this is a relatively simple one compared to others that have been found. This is the kind of a picture, an image of maybe what's going on. What's nice about this Escher print is that locally everything's fine, right? So if you just look at a certain area, there's nothing strange going on. Similarly, with the hidden variables assignments, if I just look at a particular basis, I can assign values, no problem. The problem here is with the global structure, and similarly, I can't basically assign zeros and ones such that everything matches together properly, where I can have wherever 2 things overlap, they get the same values. I can sort of change things locally, but there's always going to be a mismatch somewhere in this set. When you say do it, I mean, what we're trying to do here is explain the outcomes of quantum measurements as being deterministically fixed by something deeper. What you can, we've sort of defined that precisely and just asked, can we have that sort of model? And the answer is no. What you could do is say, well, let's give up on this non-contextuality. Let's imagine that the outcome you get for a particular ray does depend on what basis it's measured as part of. Or you could try to give up on the idea of hidden variables. Maybe give up on the idea of determinism, that the outcomes are fixed deterministically. I'll come back to that last one. This, incidentally, is what the original proof looked like. So rather than those 9 bases, I can't remember how many bases there were here, but there were 117 rays in all, and this was the diagram. So every node in this diagram is a ray, and lines represent orthogonality. And so with this diagram, you can also prove a contradiction, but it's much more complicated. Yes?
So I didn't get, why did you say in each quadruple there should be only one of them?
So the idea, if I go all the way back here, was, if I look at a particular lambda, particular ontic state, it's going to say that one of the outcomes occurs and the others don't occur if the outcome is fixed deterministically by the ontic state. So that means that for every ontic state and every basis, if I assign zeros and ones, the 1 signifies that this is the outcome that will occur for that ontic state, and the zeros signify that this outcome will not occur. So if I'm in a 4-dimensional space, then I would have 4 vectors, and I would say I need to assign 3 zeros and a single 1, and that 1 tells me which of those 4 vectors would occur if I did a measurement for the ontic state lambda. And so that's why I demand here that, so the assumption is, the hypothesis is, there is an ontic state lambda, and it fixes the outcome of all these measurements. Even though in quantum mechanics we're told we can't do these measurements simultaneously, let's ask whether it's possible to find an underlying hidden variable description that assigns a deterministic outcome to each one of these measurements. And furthermore, if a particular ray appears in 2 measurements, it gets the same value, right? So if the ontic state says that this outcome will occur for the first measurement, if the first measurement were to be implemented, then that same ontic state also says that this outcome would occur if the second measurement were implemented. And the reason that that's plausible is because if I look at the probability of getting the first outcome in these 2 measurements, then no matter how I've prepared the system, I always find that that probability is the same. So maybe it means that they represent the same property, and they should be assigned the same value by the ontic state. OK, I'm going to be showing you more different kinds of proofs. So there may be other proofs that you find more appealing. But first, let me give you another couple of ways of defining this notion. So there's all these different ways of defining it that amount to the same thing. Different proofs make use of different versions of the definition. So let's, instead of talking about measurements that correspond to bases in the Hilbert space, and therefore outcomes correspond to rays, let's imagine measurements where the outcomes correspond to projectors. So again, we haven't moved out of the realm of projective measurements. We've just now allowed that some of these projectors might not have rank 1. They might not be projectors onto rays. So if we're talking about such measurements, then we can define non-contextuality as follows. For every ontic state lambda, every projector pi is assigned a value 0 or 1, regardless of how it's measured. So again, if I have 2 measurements, they both are associated with a set of projectors. They might have some projector in common. And so a non-contextual hidden variable model says, well, first of all, that all those projectors should receive values 0 and 1, specifying which of those projectors would occur, which outcome would occur if you were to do a measurement for ontic state lambda. And if the same projector appears in 2 measurements, it should get the same value. So we can write the value that's assigned to projector pi by lambda as just v of pi. So I could have written a subscript lambda here if I wanted to say that it's for a particular ontic state. And if I coarse grain a measurement, right, so if I say I have a measurement, it has a bunch of outcomes. Now I want to define a new measurement which just lumps some of these outcomes together and calls them a single outcome. Well, then it's clear that this is the value I should assign to the sum of the projectors, the coarse-grained outcome, given the values I assigned to the individual outcomes. Sort of straightforward, because if all the outcomes that I'm lumping together are assigned value 0, then I should assign value 0 to the coarse-grained outcome. And if one of them gets assigned the value 1, of course, at most one of them could be assigned the value 1. So if one of them gets assigned the value 1, then the coarse-grained outcome gets assigned the value 1. So we should assume that. And then finally, every measurement has some outcome. So if I coarse-grain all the outcomes, which just corresponds to asking, did the measurement occur? Did some outcome happen? I should say, then the answer is always yes, some outcome happened. So the value I assign to identity, the kind of trivial, fully coarse-grained outcome, has to be 1. So again, all of this is just another way of saying what I've said before in the context of vectors. And now I can say something about what a traditional non-contextual hidden variable model would say about the values you should assign to Hermitian operators. So I've sort of gone vectors, projectors. Now we're at Hermitian operators. So in the textbook way of doing quantum mechanics, every measurement is associated with a Hermitian operator. And then if you have 3 Hermitian operators, A, B, and C, and A and B commute, A and C commute, but B and C don't commute. So that says I could measure A and B together, and I could measure A and C together, but I can't measure B and C together. Then it says that the value that the hidden variables should assign to A, so in one of these hidden variable models, your Hermitian operator is going to be assigned a value, one of its eigenvalues, and it's basically the value that you would obtain if you did the measurement for that ontic state. So the value assigned to A should be independent of whether it's measured together with B or together with C. So in this case, the context is which of these 2 measurements you're doing together with A. You can't do them both, because B and C can't be measured simultaneously. And so you could imagine that you might get assigned a different value to A depending on whether you measured it with B or C. But the assumption of non-contextuality is that you don't. Because again, if you measure A together with B, and you ask, what's the probability that I get value A in my measurement? Then you find that it's exactly the same as the probability of getting value little a if you'd measured it together with C. You never see a difference in the statistics of outcomes for your A measurement based on whether you've measured it with B or C. And that suggests that you're really measuring the same property. So a hidden variable model should assign the same value to A in those 2 contexts. OK, so let me just show you how strictly that follows from the last definition. So if you measure a Hermitian operator A, you're really measuring the projectors onto the eigenspaces of A. So I'll call those pi little a. You know, we talked in the first week about how the set of projectors represents the measurement, and the eigenvalues are just a conventional way of labeling the outcomes. So if A is written in terms of its spectral resolution, so these are the eigenvalues, and these are the projectors onto the eigenspaces, then it makes sense to say that we can assign as a value to A just whichever eigenvalue corresponds to the projector that's assigned value 1 by the hidden variables. Right? So remember that so these pi a's form a resolution of identity. So the values of the pi a's are such that one of them receives value 1 and all the others receive value 0. That's the pi a that you would get if you did a measurement for that ontic state. And then this sum just says pick out the eigenvalue corresponding to the outcome you get. So the values of a Hermitian operator are confined to the eigenvalues, and they correspond to the one that's specified by the ontic state. OK, so now if you measure A together with B, then what you're really doing is measuring the projectors onto the joint eigenspaces of A and B. Let me call those pi sub little a little b. And coarse graining over the B outcome. So this is just one way of measuring the observable A. Measure it with B, and then ignore the outcome of the B measurement. So ignoring the outcome of the B measurement corresponds to just coarse graining these projectors here over the different possible values for little b. So that gives me pi a. But another way of getting pi a is to measure it together with C. So then you're measuring these other projectors. These are the joint eigenspaces of A and C. And then you coarse grain over C, and you get pi a back. So this is a bit like in that very early example. I hope it's not too far back. Yeah, here. Right. You know, when I measure this basis or this basis, and then I coarse grain this outcome, or I coarse grain this outcome, I'm left with the same pair of projectors, the projector onto this ray and the projector onto the space orthogonal to it. So I can start, so you can think of this as A could be something whose eigenspaces are this vector and this plane. B might be something whose eigenspaces are this vector, and this vector, whereas C would be, you know, these eigenspaces here. OK, good. So these are two ways of measuring A, either with B or with C. And the point is that on the last slide, the definition of non-contextuality said that the value you assign to pi a should be independent of the context. It doesn't matter which way you measure it. You should get the same value, regardless of whether you've done it this way or this way. And therefore, this v of pi a value here doesn't depend on whether you've measured a together with b or together with c. So the value you assign to a should also be independent of that context. Okay, so now you've seen 4 different flavors of this definition. Let me give you a proof that you cannot have a non-contextual hidden variable model of quantum theory that uses this last definition. So to do that, I need one extra piece of information, which is that functional relationships that hold among commuting Hermitian operators are also hold for their values. So L, M, N, ... This is just a set of commuting Hermitian operators, things you can measure at the same time. And whatever functional relationship holds among them, so I've just written that as f of these guys is equal to 0. Any functional relationship can always be written in that way. Well, the same functional relationship has to hold among the values that are assigned to these guys in a hidden variable model. The reason is, or the simplest proof of this, is that if you want to know what are the sets of eigenvalues that can be simultaneously assigned to these different Hermitian operators, because these values here are all drawn from the eigenspectra of these Hermitian operators, then it's just specified by the joint eigenstates of these Hermitian operators. So if I just act the first equation on every one of the joint eigenstates of these operators, the left-hand side acting on the joint operator will become this. It'll just pull out the eigenvalues for each of these guys. And so I'll have proven that the functional relationship also holds for the joint eigenvalues. OK, so now on to the proof. So this is a particularly simple proof. It's called Merman's magic square version of the Cauchy-Specker theorem. It also happens in a 4-dimensional Hilbert space. And this time you should think of it as 2 2-dimensional Hilbert spaces, 2 qubits. And so here are the measurements that are involved. So here, x and y and z represent the Pauli operators. So Pauli z, Pauli x, Pauli y. And the indices 1 and 2 represent qubit 1 and qubit 2. So this is a measurement of Pauli x on qubit 1. If I wanted to, I could have written x1 tensor identity on 2, meaning that the measurement on qubit 2 is trivial. And so on. So these guys here are measurements of x1 tensor x2. So that means that all that measurement returns is a value, plus or minus 1, which tells you about the correlation between x1 and x2. So either they're correlated, plus 1, or anti-correlated, minus 1. And what you find is that in this square, the observables in a row commute with one another. So x1 commutes with x2, and each one of them commutes with x1 tensor x2. Similarly here, this one's a little bit harder to see, but using the commutation relations of the Paulis, you can verify that these 3 guys commute as well. And similarly, all the columns form commuting sets. So x1 commutes with y2. Well, they're on different Hilbert spaces, so it doesn't matter that you have x and y. x1 commutes with y2, and they both commute with x1 tensor y2. Similarly here. And then again, this is the only non-trivial one to check, but you can verify that those 3 guys commute as well. And if you multiply the observables in a row, so x1 times x2 times x1 tensor x2, well, you just get x1 squared, x2 squared. And maybe you saw at some point that all the Pauli matrices, when I square them, give me identity. And therefore, I just get identity if I multiply these 3 guys together. And similarly, if I multiply this row together, I get identity. If I multiply this row together, you get sort of x times y is minus I times z, or sorry, is I times z, and then y times x is minus I times z. So I get an I and a minus I, which give plus 1, and a z squared, z1 squared, z2 squared. I get identity. The only difference is it's the same with this column, same with this column, and then finally with this column here, x times y is I times z1 times z1 is I z1 squared, so that's just complex I, and I get another I, and I squared is minus 1. So this guy here gives minus identity. So I've written it here. Okay, so now we have a bunch of functional relations that hold among the quantum observables. And we saw in the last slide that whatever functional relations hold have to hold among the values assigned to those observables in a non-contextual invariable model. So whatever value I assign to each one of these guys here, the values across the first row have to multiply to 1. Here I've just taken the value of the right-hand side. But as we saw just a few slides back, the value assigned to identity has to be 1. So we assign the value identity to 1 to identity. And then here, minus identity has to be assigned the value minus 1. Another way of seeing it is just to say, look, the only eigenvalue of identity is 1, and the only eigenvalue of minus identity is minus 1. And the values that we assign to these things have to be taken from their eigenspectrum. So a traditional non-contextual hidden variable model has to satisfy all these equations. And now I can derive a contradiction. Can anyone see what it is who hasn't seen the magic square proof before? So if you already know how it works, don't speak up. Let me point out that the critical assumption, the assumption of non-contextuality, is appearing here in the following way, that when I consider the value assigned to x1 in this row, it's the same as the value that's assigned to x1 when I consider it as part of this column. So v of x1 here has exactly the same value as v of x1 here. So, Ali, you have a... Yes?
If the value is exactly the same, then, well, if we multiply all the things in this table, should we get the same result if we do it, in the rows or if we do it in the columns? So, yeah, it's not this.
Exactly. So if you multiply, say, all these 9 values together, that corresponds to just multiplying these things sort of row-wise. These 3 equations tell me that product should be plus 1. But if I multiply the same 9 values together, but now considered as these sets, these 3 equations tell me that the product should be minus 1. And that's a contradiction. Another way of seeing it is just that if you multiply the left-hand sides of all these equations together, then because every element appears twice, every element appears in one row and one column, I'll get v of x1 squared. And it doesn't matter what v of x1. If it's plus or minus 1, it squares to 1. So the product of all the left-hand sides is clearly plus 1, because everything's squared. But the product of all the right-hand sides is clearly minus 1. So it's a contradiction. So you cannot have a non-contextual deterministic assignment of values to the measurements in quantum theory. Again, just another version of the same proof. Good. So I could give you, proof after proof after proof, but it would just maybe be interesting what kinds of structures in quantum theory allow these sorts of things. But I think it's more interesting to see how it's connected to a few other ideas. So the first thing I want to point out is something I mentioned at the end of last time, that a kind of locality is an instance of non-contextuality. So you remember from the beginning of the lecture yesterday that there was a notion of local determinism, which said that the events in a particular region of space-time are completely determined by the physical states in some region that closes the backward light cone. So local determinism turns out to be an example of this notion of non-contextuality I've just described, in the particular case where the context is far away. So take this example. So it's from our proof of Bell's theorem. So take spin along the a-axis for system A, that observable, and imagine measuring it together with spin along the b-axis for system B, or the b-prime axis. Okay, so I'm putting in the identities here explicitly so that it's clear that this guy commutes with this guy and he commutes with this guy. But if I choose these axes to be different, then these guys don't commute. So that's just like that ABC scenario I talked about, where A commutes with B, A commutes with C, but B and C don't commute with one another. That's exactly what we have going on here. So the traditional notion of non-contextuality says that the value you assign to A here should be independent of whether it's measured together with B or with C. Okay, so that means that in this particular case, the value I assign to spin along the A-axis should be independent of whether it's measured together with B on the faraway system or B prime. But that's exactly what the assumption of local determinism says, because this choice of whether to measure B or B in prime is happening at space-like separation. So you could say that's one case where this assumption of context independence is really solid, because you would hope that that sort of difference, which is happening at space-like separation, couldn't influence the value assigned to this guy, the deterministic value assigned to him. So we conclude that V of SA has to be the same for the two contexts by local determinism. Or rather, in this case, non-contextuality is local determinism because the contexts are far away. The general notion of non-contextuality is one where the context might not be remote. Okay, so locality is a particular kind of non-contextuality. One way to think about it is that sort of locality is a more reasonable assumption, and therefore, it's more striking that we have Bell's theorem than that we have a Cauchy-Specker theorem. On the other hand, you might say, well, non-contextuality is the kind of more generic phenomena, and non-locality is just one particular instance of that phenomena that is particularly surprising. But it's, to really understand what's going on, you should understand the more general phenomena. Questions? Okay, let me skip over the next slide. I was going to talk about another connection between locality and non-contextuality, but I think it's better to just move on. I guess I didn't say this, that it follows that if you have a proof of the impossibility of a locally deterministic model, then you also have a proof of the impossibility of one of these traditional non-contextual models. All right, let me skip this. I want to, in the second half of the lecture, talk a bit about how to make the notion of non-contextuality more operational. So what are the problems that you might have with the notion as I've defined it so far? Well, one thing is we've only been talking about these sharp measurements. So sharp is a word that's sometimes used in place of projective. So we've only been talking about projective measurements, and we saw in the first week that the most general kind of measurement is a POVM. So you might have asked, what should we say about POVM measurements? Is there a notion of non-contextuality for them? Secondly, we've only been talking about deterministic hidden variable models, one wherein the outcome of the measurement is fixed by the ontic state. But when we introduced hidden variable models, we imagined more general types, where the outcome of the measurement might only be determined probabilistically by the ontic state. So again, the question is, could we have a notion of non-contextuality for those more general kinds of hidden variable models? And then thirdly, maybe most importantly, everything I've said so far today has been specific to quantum theory. It's been about the representation of vectors and Hermitian operators. And those are objects that only make sense in the context of quantum theory. If I'm looking at a theory that doesn't use Hilbert space, I can't use those definitions I showed you. And that's unlike what we see for Bell's theorem, where Bell started with a notion of local causality that could be applied to any theory. It didn't make reference to the quantum formalism at all. So what you'd prefer to have is a notion of non-contextuality that didn't make reference to the quantum formalism, such that for any way the world was, any operational theory, we could ask, does it admit of a non-contextual hidden variable model or not? Okay, that's what I've just said here. If we had an operational notion, then we could ask whether any given operational theory admits of a non-contextual model. So if quantum theory turns out to be wrong and some other theory replaces it, we could ask of that theory, does it admit of a non-contextual hidden variable model, just as we ask whether any theory admits of a local model. But furthermore, if you have some experimental data, then you can just ask directly of that data, can it be explained by such a model? So that's what we have in the context of Bell experiments. You go to the lab, you collect some data, and your conclusion, if it violates a Bell inequality, is that there are two sorts of theories. There are the theories that satisfy Bell inequalities, and there are the theories that violate Bell inequalities. And our experiment has shown that whatever theory of the world is true, it must be one of the ones that violate Bell inequalities. Quantum theory is one of them, But maybe quantum theory is wrong. What we know is that whatever theory is going to replace quantum theory, because of the Bell experiments, it can't be one of the local theories. It still has to be a non-local theory. And so you might, if you had an operational notion of non-contextuality, and then you showed an experiment that violated that, such that the experimental data could not be explained by a non-contextual hidden variable model, then you'd be able to say that whatever theory is true of the world, it must be contextual. It must fail to be non-contextual. So we sometimes say it's contextual, even if quantum theory is wrong. So there's a strong motivation to try to make the notion of non-contextuality as operational and theory independent as the notion of locality that Bell introduced. Okay, so I'm going to tell you about such an operational notion. And I think it also gives one of the nice things about using operationalism as a kind of methodology for making progress, much the way that Einstein did in 1905 when he got clear on the notion of simultaneity, it kind of helps you understand better what's going on. So I think at the end of this, hopefully you'll have a better notion of what non-contextuality means. Because it's a very slippery concept. It's probably one of the hardest concepts you'll see in this course is the notion of non-contextuality. Okay, so let me remind you what an ontological model of an operational theory is. So by operational theory, I just meant a theory that makes predictions about the outcomes of experiments. And now an ontological model is one of these models that posits a space of ontic states, and it represents it represents a preparation procedure by some distribution over that space of ontic states. It could be a delta distribution, but more generally it could be spread out, which just means that if you know everything about the preparation procedure, you still might not know everything about the state of the system that comes out. And similarly, if you have a measurement procedure in your operational theory, then you represent that by a set of indicator functions. So this function here is the probability of getting outcome 1, given that the ontic state was lambda. And now I allow these things to not necessarily be deterministic, right? So here in this region, for example, the probability of getting outcome 1 and outcome 2 are both non-zero for that lambda. So the physical state of the system now is not fixing what the outcome is in this kind of model. And then finally, as we've seen before, whatever your operational theory predicts, right, it's going to, at the minimum, what an operational theory does is it predicts outcomes of probabilities for different outcomes of your measurement M when you've prepared P. Well, your ontological model has to reproduce those predictions. So it has to say that if I take the probability of outcome K given lambda times the probability of lambda given P, integrated over lambda, I should get these probabilities back. So you've already seen that. It's just review. Okay, so what is a non-contextual ontological model for an operational theory? So I'm just going to give you a sort of a heuristic notion, and then I'll go into more detail. So this is just meant to give you a flavor of the definition. So an ontological model is non-contextual if operational equivalence of two experimental procedures implies that they get equivalent representations in the ontological model. So roughly speaking, if you can't see the difference between two experimental procedures in the lab, say none of the statistics differ, then you should represent them in the same way in the model. Okay, let me be more explicit about that. So what do I mean precisely by this operational equivalence? So say you have in the lab a whole bunch of different preparation procedures you could do. So inside each of these boxes is a different kind of list of instructions. Maybe you've got it automated. And over here you have a whole bunch of measurements you might do. Well, you can take two of these preparations, or take one of them, put it in front of every measurement device, calculate a whole lot of statistics, and find what the probability distribution of the outcomes for that measurement is. And then do it again for the next measurement, and get a long list of the statistics for every possible measurement you have. That will be a characterization of this preparation procedure, as we've seen before. And what you might find is that these two preparation procedures give you exactly the same statistics for all measurements. So that means that if I may have done very different things inside these boxes, but if that's hidden from you, these are black boxes, you don't know what goes inside them, then you can't distinguish what's going on here from what's going on here, right? That every measurement you do will be consistent with the one preparation or the other. So that's what I mean by operational equivalence of preparation procedures. These two preparation procedures give the same statistics of outcomes for every measurement. In that sense, they're equivalent. They're not equivalent in the sense that they correspond to doing different things in the lab, but from the perspective of the statistics you get, they're equivalent. So I could sort all of my preparation procedures into equivalence classes now based on the set of measurements. So just to give you an equation, I say that preparation procedure P is operationally equivalent to P prime if, for all measurements and for all outcomes, the probability of outcome K for measurement M is the same for P and P prime. OK, so this is a difference of equivalence class. And now the notion of context in this operational approach is just whatever's left over. So any differences that are left over will be called differences of context. So a totally trivial example would be, if I prepared something Z spin up by filtering, say the top beam of Stern-Gerlach apparatus, and the first apparatus is painted red and the second apparatus is painted blue, well, that's clearly just a difference of context because the future statistics are not going to depend on the color I painted the apparatus. Less trivial would be if I use a piece of Polaroid to pick out horizontal polarization, as opposed to a birefringent crystal and then filter out one of the beams coming out of the birefringent crystal. Those are very different ways of preparing horizontal polarization. But you find that all your future measurements don't distinguish those two ways of preparing horizontal preparation. So the difference between birefringent crystal and polarizer is a difference of context. There are also non-trivial differences of context in quantum mechanics. So now I've switched from talking about a general theory. I'm going to just tell you about one example in quantum mechanics. So different equivalence classes in quantum mechanics are represented by different density operators. We've seen that because if I have two different density operators, there's always some measurement in quantum mechanics that will have different statistics. Okay, density operators really are meant to be a compression of all the experimental statistics you might see. So any two different density operators, there's some measurement where they make different predictions. And then differences that remain, differences in quantum theory that we would call differences of context, include things like how you mixed two states together to get the completely mixed state. So way back in the first week, we saw that there's this multiplicity of ways of getting the complete mixed state. I could take an equal mixture of Z spin up and Z spin down, or I could take an equal mixture of X spin up and X spin down. And those are very different things. But if I put them in a black box, so this black box flips a coin and either prepares one of the two Z eigenstates, the other black box flips a coin and prepares one of the X eigenstates. And then I ask you, I just give you outputs from the black box. And I let you do any measurement you like on them. And I say, which was it? There's nothing you can do. Every measurement you do is consistent with this density operator, has exactly the same statistics. And so you just can't tell those two boxes apart. So that's a notion of context. Which pure state ensemble you used to generate that mixed state is an example of a preparation context. OK, another example was the fact that there are many purifications. So I could prepare two qubits entangled and then ignore one of them and give you the other. And again, whether I prepared this entangled state or this entangled state, if I just give you the first qubit, there's nothing you can do to figure out which of those preparations was done. So that's another example of a context. So in this language, a preparation non-contextual model is one that assigns exactly the same distribution over the ontic states for all the preparations in a given equivalence class. So it says, look, where I was in this equivalence class doesn't make any difference to the statistics of future measurements. So I should assume, one way to explain that, one natural way to explain that, is because they're preparing exactly the same distribution over the ontic states. If that happened, then very clearly, none of these measurements would be able to tell the difference between these guys. So it's one way of explaining it. It's not the only way that you might explain it, but it's one way. It's a natural way. The alternative, which I'll call a preparation contextual model, is that you have different distributions associated with preparations that are in the same equivalence class. So how could you possibly do justice to the fact that these two preparations get exactly the same statistics? Well, maybe these measurements are all somewhat noisy, right? So that all your measurements are kind of fuzzy enough that they can't tell the difference between these two distributions. So if that were the case, then it would be possible that these things are associated with different distributions even though all the statistics of every future measurement's the same. But it's sort of an awkward explanation. It says that there's a difference in reality that we will never see in any of our experiments. None of our experiments can see the difference between these guys. So you might say, well, that isn't a particularly elegant explanation to start with. This other explanation seems more natural, so it seems like a good way to go. You can make a similar definition of measurement non-contextuality. So, I should say, this is ultimately then the definition of what I'll call a preparation non-contextual model. If your P and P prime are operationally equivalent, so they assign the same probabilities to outcomes for all measurements, then they assign the same probability distribution over the ontic states. Okay, so sameness of these operational probabilities implies sameness of the realist ontological probabilities. Okay, actually, before I move on to measurements, I wanted to give you an example of the two kinds of theories. And you've already seen these, so it works nicely. Say you just take 5 operational states of a qubit. So Z up, Z down, X up, X down, and the completely mixed state. So you know that the completely mixed state can be made as a mixture of these two or as a mixture of these two. Now, this week we saw 2 models that can do justice to the statistics for these kinds of guys. In one model, this one here, you had an ontic state space that had just 4 elements. These were the distributions that corresponded to these guys. So these, remember, were sort of uniform distributions over these squares. Another way of drawing it would be, label the 4 squares and then just draw the distributions out like this. And what you found is that the mixture of these 2 guys was the uniform distribution over all 4, and the mixture of these 2 guys was the uniform distribution. That's preparation non-contextual. It says, look, the reason you can't tell the difference between the mixture of these guys and the mixture of these guys is because it's exactly the same distribution over the hidden variables. Obviously, you won't be able to see any difference. But we looked at another model, the Cauchy-Specker 1967 model, which said that the distribution you assign with this state is a distribution on a sphere of ontic states, which is peaked at the North Pole and goes to 0 at the equator. And the Z spin down is peaked down here, X spin up, X spin down. And now if you take the equal mixture of these guys, you get this. The equal mixture of these guys, you get that. They're different. But you didn't see this difference in the measurements because if you'll recall, the measurements in this theory corresponded to asking, is the ontic state in one hemisphere or the opposite hemisphere? And if you do the math, you find that for every division of the sphere into 2 hemispheres, the integral of this distribution and the integral of this distribution are exactly the same. So that's precisely the kind of sort of noisiness in your measurements that would make it such that you can't tell the difference between 2 different distributions. So that's a possible explanation, but it's contextual because the way you represent the identity over 2 quantum state is different depending on which pure state ensemble was used to form it. So is that clear? Okay. Let's talk about measurement non-contextuality. So again, I can sort my measurement procedures into equivalence classes. So 2 measurements are going to be in the same equivalence class if, when I calculate the statistics for this guy for every single preparation, I get exactly the same thing as when I calculate the statistics for the second guy relative to every single preparation. So again, if I put one of these 2 in a black box and ask you to figure out which, you couldn't do it. And whatever differences are left over are differences of context. So what are some examples? Well, we've already seen some in this lecture. If I have a 3-dimensional Hilbert space and I consider this measurement here followed by coarse graining these 2 outcomes, so just record, let the measurement outputs whether it was psi1 or one of the other 2 guys. And this measurement here, whether it's psi1 or one of these 2 guys, psi2 prime and psi3 prime, those guys are completely indistinguishable once I've done the coarse graining. They just correspond to the same pair of projectors, right? So they're both correspond to this projective value measured. Projector onto psi1 versus identity minus projector onto psi1. The only difference is in how we decompose this rank 2 operator, either in the psi2, psi3 basis or the psi2 prime, psi3 prime basis. That's exactly like this ambiguity in the decomposition of the completely mixed state into 2 different ensembles. But now it's at the level of the projectors in the measurement. So this is a notion of a measurement context. Another example comes from POVMs. So now we can really talk about POVMs. So remember that sometimes you can represent POVM elements as points in the Bloch sphere. So it turns out if I consider the POVM whose two outcomes correspond to these 2 points in the Bloch sphere, then there's two ways of measuring it, which are sort of roughly depicted here. So one way would be take the pure version of this measurement, so the projectors here, and mix it with the kind of coin flip, identity over 2, identity over 2. And that sort of brings you in, as we saw in the first week. Another way to do it would be to do this measurement and this measurement. So this pair of outcomes for the first measurement, this pair of outcomes for the second measurement, and just record whether you got the first or the second outcome. So if you got one of the two first outcomes, then your overall operator associated with that is this guy. If you got one of the other two outcomes, it's this guy. So again, there are multiple ways of implementing a given POVM, just as there are multiple ways of preparing a given mixed state. Here's what it looks like in terms of equations. So the POVM is just some operator E versus identity minus E. But I can think of that operator E as a coarse graining or a mixture of the coin flip POVM with the projector onto the pi by 4 state in the Bloch sphere. Or I can think of it as a coarse graining of the measurement, or sorry, a mixture of the measurement along Z spin and the measurement along X spin. So again, this difference, although it's a perfectly well-defined difference of what you do in the lab, is a difference of context because none of your statistics will see the difference between these two sorts of measurements. Okay, so what's a measurement non-contextual model? It's just one that assigns a set of indicator functions. And it's the same set of indicator functions whether it's this measurement or that measurement. So if two measurements only differ in context and they're in the same equivalence class, then they should be represented by the same set of indicator functions. They might be non-deterministic, but it's the same for both. Whereas in a measurement contextual model, you might have different indicator functions for the two measurements. Here I'm imagining that each of these measurements has two outcomes. So again, how could this be? How could it have two different sets of indicator functions and still the statistics of these two measurements are exactly the same? Well, it's because maybe these probability distributions over the ontic states are sufficiently spread out that the fine details of these two guys don't register. And so you can't tell the difference between those guys using those sorts of distributions. Okay, so given these two notions of non-contextuality I've described, you could say, well, it only makes sense to have a kind of generalized notion of non-contextuality, which really asks for both. The reason being that although measurement non-contextuality is closer to the traditional notion, whatever reasons you think that this might be natural, you could give the same reasons for saying that preparation non-contextuality is natural. And if you think this is unnatural, then you'll think both are unnatural. And then if you ask, well, why should we think this to be plausible at all? I think the best answer to that is there's a kind of methodological principle that is used in physics sometimes. An example of it would be Einstein's equivalence principle. So you remember, Einstein said, look, you cannot tell the difference between being in an elevator that's at rest in a gravitational field and being in an elevator that's in free space accelerating. Therefore, we should assume that in reality, there is no difference between those two scenarios. Ontologically, they're the same. And he tried to come up with a theory where that was indeed the case. And so you might say, well, there's sort of a general principle here that if a difference in the setup is not distinguished in the observable phenomena, then it shouldn't be distinguished in the ontological picture either. And so that's what non-contextuality in some sense has been trying to do. It said whenever two preparations are not distinguished in terms of the observable phenomena they lead to, the statistics of measurements, then we should assume that the ensemble of ontic states that they prepare are exactly the same. So they're not distinguished in the ontological model either. Good. So I have, I think I will just start next time with a particular proof that you cannot have a preparation non-contextual invariable model of quantum theory. And then I'll say a little bit more about measurement non-contextuality. And then we're going to move on to de Broglie-Bohm interpretation and the other interpretations of quantum theory. So are there any questions about what I talked about today? Yes?
Next time, but
Yep.
so you said you can't have okay, so preparations are contextual.
That's
but
right.
Are measurements contextual?
So that's a bit, that'll sort of come up next time, that strictly speaking, when I define a measurement non-contextual model, it doesn't actually match with the traditional definition I gave you, because so far there's no determinism. I haven't demanded that these outcomes be deterministic, given the ontic state. And so, strictly speaking, this notion of measurement non-contextuality is a revision on the traditional notion. It would say that even for projective measurements, I should ask whether they're represented by the same set of indicator functions, but possibly not deterministic. However, if you, so this is a bit subtle, but if you assume preparation non-contextuality in the background, you say, look, if I'm going to assume measurement non-contextuality, I may as well assume preparation non-contextuality as well. If you assume that, then you can actually prove that for projective measurements, these indicator functions have to be sharp. They have to have value 0, 1. So then you recover the traditional notion. So strictly speaking, this generalized notion, operational notion of non-contextuality I gave you, does imply the traditional notion for projective measurements. And so every proof, traditional proof, becomes a proof of the impossibility of achieving this general notion of non-contextuality. So yes, yeah, in a sense, you also cannot have measurement non-contextuality because, well, I guess I said that wrong. I mean, if you were willing to sort of break this and say, I'm interested in models that are purely measurement non-contextual, but I don't care about the preparations. So I argued here that that's sort of an unnatural place to be because the reasons you give for one are very similar to the reasons you give for the other. But suppose you want to do that. Then it turns out you can find a measurement non-contextual model. And the orthodox model that we talked about in class is an example. For every projector, it had the same distribution over the state space. It failed to be deterministic. But because the state space of that model were the pure quantum states, you found that preparation non-contextuality failed. So let me remind you how that model worked. It was, if I have a state psi, or if I have a state that's, say, of a qubit that's plus along the n-axis, then the state space was just the surface of the Bloch sphere, and the distribution was a delta function at the North Pole. And then the measurement onto plus m was something that was peaked along the plus m direction here, and it sort of went to 0 on the opposite side of the Bloch sphere with a cosine fall off. So it turns out if you generalize this to higher dimensions, the way you represent the projector onto a given state is exactly the same for no matter what basis it is a part of. But when I look at something like preparation non-contextuality, I find that the mixture of plus n and minus n, so let's say I do it for z, the mixture of z up and z down will be a doubly peaked distribution here and here, whereas the mixture of x up and x down will be doubly peaked here and here, and they're not the same. And so I have preparation contextuality in this model. Good. And in fact, you can prove in general that every model has to be preparation contextual. There are ways of salvaging measurement non-contextuality, like in this guy, but there's no ways of salvaging preparation contextuality. Other questions? Okay, let's end there.